Okay, so one quick note, 'cause I saw this a little bit. If you have something, this is a great example of the last topical guide objective. If I don't have end TGO after the line, it's just that line. So don't feel like you have to write all the rest of this. It's just define exception. Exception is an unscheduled event that disrupts program flow. Okay. Also, I did a little bit of rearranging of the lecture notes and adding a couple things I felt would present the material a little better. So I'm going to update the TGO list on Blackboard after lecture today. So as you're going through that. So we briefly discussed what an exception was. And we're going to go in a lot more detail, especially when we get into pipelining and eventually when we get into the Tensilica processor, going into exceptions and interrupts and how that works. So we kind of briefly talked about what happens when we can't complete an instruction, right? So what ends up happening is that we have what's known as an exception program counter. We talked about how when you the MIP screen sheet, I'm sorry, I'm double checking to make sure that I started the recording. Okay, the computer's struggle busting today. So the exception program counter, we have the current status of the program, and we then have the move from system control MFC to 0, which we're going to discuss in a little more detail. But the whole idea is we take the current register and it stores the value from the specific source registers into the destination registers, and we want to be able to indicate what the instruction type was, what the instruction actually was that caused us this error, what happens that caused the unscheduled event. If we had an overflow we can't account for. In some cases, if the compiler creates an opcode that isn't actually in the instruction set, what ends up happening is we can't execute that program, right? If I tell you that your homework assignment is right, you can't do that. So you need to go, your exception is raising your hand and going, Dr. Morrison, what you just said is literal gibberish. Right? And so that's the same thing that goes on in the data path. If there's no opcode that correlates to what comes out of the instruction memory, it's literally like me to, right? That's exactly what it is. So we have to tell the computer to stop, stave the current status of the program, and then it's up to the operating system. The operating system works on solving the problem, in which case it's sent back to the data path. So in order to account for this specific instance of overflow, often we want to be able to go past this specific range of -2 to the 31 and 2 to the 31 minus 1. So what we're going to be doing is later in lecture we're going to be talking about IEEE 754 format. Before that, first I want to go into kind of reviewing what is actually physically going on in addition. Do you guys cover adders in 235? Okay, so a lot of this is going to be some brief review. So 2.5, the topical guide objective. Let me zoom out here for a second. The full thing for 2.5 is to draw full adder circuit as well as the equations. I found that in past times teaching this course that students have either kind of forgotten how this works, or specifically what is really important is the equation, especially when you get into 485 and microprocessor design. When you do Verilog as well, we're going to be doing it in this course as well as 386, is being able to code this up. So you actually have to know how it works. So you have to have A XOR B XOR C. In this specific case, even though that you know that A XOR B XOR C doesn't need brackets in order for you to be able to perform it mathematically, the reason I have it in brackets is to show you, is to reinforce how it's physically being done, right? So in this case, A XOR B is done first physically, and then the result XOR C is what's done next. So in this case, the result of A XOR B is also ANDed with C, and then we are ORing it with A and B on the output. Basically a review, right? So then the question becomes, how do we're talking about high performance execution of compiled code, and we're looking for ways to do trade-off. So in 235, you cover subtractors? No? Okay, so there is a device called a subtractor. And it's a completely different set of equations. And often, if you're going to do a high area implementation, if you're trying to have an arithmetic logic unit that does addition and subtraction, you do a full adder, full subtractor, multiplexer, right? To multiplex the result. However, that multiplies the area by 2. So because if you're doing a 32-bit addition and a 32-bit subtraction, you then have 32 full adders, 32 full subtractors, and that just doubles your area, and there's a much more efficient way to do it, which is what we're doing here. So what we're going to do first is we're just basically doing 2's complement physically. There's a reason, so you have 1's complement and 2's complement. One of the reasons why we do 2's complement here is because you can actually significantly reduce the amount of area you need to implement an adder and subtractor at the same time. So what we're doing is we invert, if we're actually, so in order to do the math and to justify why it is that we're taking an XOR gate on each input, what we do is we know that A and B, or A subtraction B, is just the same as A not B, A plus not B, right? So in order to obtain 2's complement, we know that we invert B and add 1, correct? So therefore, if we use the initial carry bit as a 1 instead of a 0, like you know how you carry in for addition, you have carry in and carry out. So if we set the value as 1, therefore, A or not B and 1 is just basically equal to A minus B. So if we invert the value of B and add 1, we can do that. Now, there's a simple way to do that. If we do carry in is equal to 1, so we'd say add sub is our bit, right? Initial bit here, and I'll scroll down for the rest of TGO 2.7. But basically, if the addition is 0, if we're doing addition, that means we want our initial carry in to be 0, right? So 1 plus 1, you don't want to have a 1 carry in, or else you're getting all kinds of funky values. Here we said that we want the carry in to be 1 initially for subtraction, right? So basically, setting add to 0 and subtract to 1 basically means that we have as a control signal to the initial CN, right? And as I've kind of been alluding to, the opcode and the controller produce control signals which dictate whether or not we want to do an addition or subtraction. You remember when I briefly went over that MIP screen sheet that we had 2 0 hex was addition and 2 2 hex was subtraction? And so that's a difference of 1 bit. So that's where this comes from. So this, still a little bit of magic, but that's where that's coming from. So what we've done by doing this mathematical proof in TGO 2.6 is demonstrate that first, what I can do is I can use the control signal that's generated for the instruction, that's generated by the compiler. So we're literally having a compiler-driven encoding of the micro engine. And so I have my opcode generate that bit to make the difference. And then, in order to invert all the bits, if I just put that same 1 bit as the input to an XOR gate, the inversion will come out on the other side, right? So instead of having to do all of these distant adder and subtractors, I just add in an inversion, I add in an XOR gate to a bunch of full adders. And so this TGO 2.7 is a 4-bit full adder. And of course, if you're doing 32 bits, 64 bits, you're just, instead of having to add in all these different ANDs and NORs and XOR gates, you're just adding one XOR gate, and using efficient design from the control signal, you're able to significantly reduce the area that you would require to be able to perform both addition and subtraction. So here in this case, what we're doing is we're just inverting B0. If it's 0, let's say if it's 0, that means the carry-in is 0. So we've done that portion of the add. And then anything XORed with 0 is just going to be that result, right? Otherwise, if we do a 1, that means we have our initial carry-in for subtraction like we need. And additionally, it allows us to also put the 1 on the input of the XOR gate, which means we're just basically turned those into inverters. So this is an example of how understanding what you need for reducing the area while simultaneously being able to perform multiple functions and taking advantage of how the control signals work will allow you to build up towards a more advanced digital system. Okay. All right, so does anybody have any questions on that? Okay, so from there, y'all familiar with ripple carry adders? Okay, so I've been significantly less yet. So the whole idea is I built a full adder, and then what I want to do is I want to take advantage of this carry in and carry out. So it's just like you're doing addition in elementary school, right? So you have 15 plus 24, 15 plus 29, right? That's a better example. So 5 plus 9 is 14, so you put a 4 there and you carry the 1, right? So likewise, it's just, 1 plus 0, it's going to be 1, but you don't carry. It's 1 plus 1, you have a 1, and then you carry, because you have a 0, but you carry the 1, right? So that becomes 2. Likewise, if you have a carry in, it becomes 1 plus 1 plus 1, which becomes 3, so you have 1, 1 on the output. So what ends up happening is each time, just like you did in elementary school, you're going to be carrying the results. You have carry in 0, something happens here, carry out, carry in, carry out, carry in, and then 32 bits is like that. So this is where, if you recall, good design requires good compromise. So what you can do is you can start playing with trade-offs in area and performance. In this case, I have what is known as a carry select adder, right? And the reason we call it a carry select adder is because I perform the initial 16 bits as normal, right? I put in the initial carry in, and then I get the 16 bits, and then that carry out is either going to be a 0 or 1, right? No matter what we do. So then what is done here is then I add in the output. Sorry, I had taken the 2 inputs. So I have bits A16 through A31 and B16 through B31. And likewise, I do the same thing here. So since I know that it has to be 0 or 1, I perform the calculation in this 16-bit ripple carry adder where the carry in is 0. I take this one where the carry in is 1. And I'm able to have, all right, if it's carry in 0, I know the result must be this. If the carry in is 1, I know the result must be this. And then what ends up happening is that when I have those 2 results here, by the time I get there, pretty much at the exact same time, I will get the actual carry in value. So if it's 0, it's like, okay, instead of having to wait and do the rest of these 16 adds, I have the result already and I can present the result. Likewise, if it's 1, the output is 1. So the trade-off is in area. So you're adding area, but the trade-off is performance. You're actually gaining significant performance here. And as it further goes on, as you want to go into more complicated designs, there are actually designs known as Kogi stone adders, where you actually are doing this all the way down to each and every bit, and it adds a lot of area. But to this day, it was developed in the 70s, but to this day, it's still known as the fastest adder design. So as you keep adding, so it seems counterintuitive because we talk about smaller is faster, but in this specific case, what you're doing is you're making decisions and allowing predictive results to be made ahead of time. So then here you can break it down into 8 and 8 and speed it up even faster, but you're adding even more area, and then down to 4, and so on. All right, so now at this point, I probably should have put comparator ahead of this, but no, I want to do this and then comparators now. So we're talking about this concept of full adders, we're calculating every bit, right? And then we have some sort of full adder result for bit 0, bit 1, bit 2, all the way bit. And so in MIPS, it's 32 bits, right? So then what I'm going to end up happening is I have a full adder, and we're doing all of the calculations simultaneously. So in this case, I have a full adder, I have a NOR calculation, an AND calculation, and an OR calculation, right? So just because I've in the past the answer's been no. Do you all know what multiplexers are? Does anybody in here not know what a multiplexer is? A lot of people. Okay, good. I'm glad you guys are on. So a multiplexer is a device that allows us to select a specific output. So a multiplexer takes in 4 bits of results, right? And then this slash in operation typically, and you'll see this as more as we get into data path design, it means it's more than 1 bit. In this specific case, in fact, how about I just bring up an empty Word document here for a moment, because you guys are actually about a half lecture already ahead of last year. Is it going to do it or not? All I need is a blank sheet. There we go. Good enough. All right, so here's the idea of a multiplexer, right? So I have 4 different inputs, right? So we'll call this S0, S1, S2, and S3. And then the device notation looks like that. So I have a 2-bit input, right? And so we typically known as the select line. And so here's the truth table. If it's select line, you can do it. All right, so select 0, select 1, and then we'll say output, right? So 0, 0, 0, 1, 1, 0, and 1, 1. So those are our inputs here. If it's 0, 0, whatever the value is on S0 is going to be our output. S1, if it's 0, 1, 1, 0, S2, and S3. So a multiplexer, and we're going to be using these a lot in data path design. So it doesn't just have to be 1 bit. In our data path, there will be several instances where you have 2 32-bit inputs, 1 bit select line, and then one of the 32-bit outputs is going to be put there, right? And in this case, when I showed you the carry select adder, that multiplexer took in 2 16-bit inputs and used the carry bit as the select line. So in that case, because it's 0, it selected one of the 2 values. When it's 1, it selects the other value. Does that make more sense? Okay, so I just realized I ran right past multiplexers and thought you guys knew that. And then I remembered in the past people have said that. So basically, the abbreviation is MUX, M-U-X. So what's going on here? You have full adder output, NOR, OR, and AND. And then the opcode tells me which value I should select. So when we get, and I'm going to be going a little bit more into arithmetic logic unit design and how these control signals are input. But in this specific data path, we have a 4-bit ALU op that goes in. It's basically an operation signal. It's not an opcode because it's not coming out of the instruction. But basically, it's the result of a calculation. It's a 4-bit value. That means that goes to the multiplexers. And so how many values can I put in, or how many values can I select from if I have a 4-bit input? 16. Why is that? You're correct. Exactly. So 2 to the 4 is 16, right? So 0, 1, 0, 1, 0, 1, 0, 1, right? So basically the same thing. Here we had a 2-bit, so we can select 4. Okay. Any other questions on multiplexers before I move on? So what ends up happening is that the result is produced in each one of these bits. And then the output is put out there. And so sometimes we are also going to be doing comparisons, right? So when I've alluded to this concept of branch equivalent circuits. So if I is less than J, what do I do? Okay. So I have to be able to generate a signal based on that result. So let me zoom it back in so then you guys can actually see what it is that I'm discussing. So this particular comparator circuit allows me to determine 1-bit outputs for if A is larger than B, if A is equal to B, and A is greater than B. Right? So in this specific case, C equals A not B, right? So what that means is we know that if it's a 1-bit comparator, that A is going to be less than B if A is 0 and B is 1. So that just becomes A not B. Likewise, we'll say E, right, is equal to A B not. So A is going to be greater than B if A is 1 and B is 0. So then, if neither of those are the case, then we just use this NOR gate, right? So if this is 0 and this is 0, what does that happen? That means 1 and 1, 1 and 1, right? Or if it's 0 and 0, 0 and 0, that means they're going to be equal. So in that case, we can just use a NOR gate to simplify that. And so what ends up happening is you have to kind of ripple it along, because overflow bits and comparator bits, I need to know that all 32 bits are the same, right? So if for some reason, and we'll just use random student unit, right? So three of you and the 4 of you are identical somehow, right? And then, but that's not the sign that all of you are equal. I have to go here, and then I check if you're equal. Then I have to go here and check if you're equal, and check if you're equal, and we're not equal because we only have one student in that. Sorry, I keep forgetting your name, Sasha, right? No. Oh, okay. So we don't have any students over here, so therefore, so that would be the same as saying like, comparator would pass, 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 and then finally we have A is greater than B. Right? So we have to check that. So the moment, we can actually determine which bits are which, but we have to figure out the most significant bit where there's a difference and figure out which one's bigger. And so this can get more complicated. So I've drawn up an example. This is not something you're going to have to do, but I wanted to combine concepts from 235. So you all remember K-maps? Okay, so that brought back to horrible memory. So what I've done is a 2-bit comparator, and I actually kind of briefly went up here and went through the whole process, drew out the whole truth table, drew out all the K-maps, and derived the equation, right? I'm not going to ask you to do this. But what ends up happening is that that's the result, okay? So if you want to kind of if you'd like to briefly pause and go over this, kind of refresh your memory. Even though I won't ask you to do this on exam, sometimes it's kind of worth your while to look over this for a split second and go, oh yeah, K-maps, I remember that, because that's something that comes up in interview questions, right? So I'm not just doing this to torture you, I promise I'm doing this to help you out. But that's the end result there. So in his case, we have A equals B, A is less than B, and A is greater than B. And here it's a 2-bit comparator. And so you can do one of two things. You can either keep doing K-maps for 4 bits, 8 bits, 16 bits, or you can do ripple carry comparators. And so the trade-off, so this, if you were to do the ripple carry, it's going to have a little more area. Like this is the most efficient because we've done the K-map reductions and figured out the efficient circuit. But as you can probably imagine, if you're doing K-maps or trying to do it much bigger or doing Quine-Mikulski reduction, you can probably figure out that these circuits they're efficient but very complex. So the reason I'm doing this is to kind of give you the idea of the trade-offs that are required in ALU design. All right, any other questions? All right, so here's how an arithmetic logic unit works on the outside. So we kind of dove into the inside. This is what adding, subtracting does. We have comparators in there. We have to do some sort of other logic depending on what the customer wants to be able to perform all the devices. So in MIPS, right, microprocessor without interlocking pipeline stages. And when we get into Tensilica later in the course, you're going to see some interlocked pipeline stages. But this is all about high performance execution of compiled code. So what we have here is we have an arithmetic logic unit. I'm sorry, let me zoom in so you can see 2.10 better. So what we have is we have an arithmetic logic unit where everything we've learned so far today is inside here. We have our 4-bit ALU operation signal that we send to the multiplexers. We have two 32-bit inputs, and we have some sort of carry-in signal, right? So in this case, the ALU operation is our carry-in. Then what happens is we have our 32-bit result, we have our overflow, and we also have this bit called 0, right? 0 is a value that is output if the result is 32 zeros. So it's a 1-bit value, and it becomes very useful for determining whether or not a value is a branch. So if we have a comparator, we compare the output to 0, and if that is the result, that bit is equal to 1. Does that make sense? And so what ends up happening is if I do a comparator and I get if I want to say A is less than B, right? Or in this case in MIPS, it's is A equal to B or A not equal to B. If it's equal and we put a 1 out in the output, that tells me that I've met my equality value and therefore I want to branch. Okay. And so I'll just read this over here. The inputs to the MIPS ALU are two 32-bit values and a 4-bit control signal. That's an ALU operation. The outputs are a 32-bit result, and then you have a 0-bit, which we just discussed, used for comparison of branch equivalent, branch not equal. And that's what those mean. For now, just understand that when we go into more detail, you'll get more familiar. And the overflow flag, as well as carry out. And so in this case, the full TGO is the definition and the drawing. All right, so what are these 4-bit values? Right? So I've alluded to this a little bit. So 2.11 is what the actual control values are. Right? So I have these 4-bit values. Now before I go into the rest of them, I do want to point out the difference here. So remember that we had addition and subtraction, right? And that you see 0, 0, 1, 0 and 0, 1, 1, 0. And so the only difference in the bit is this one, right? What do we think we use that bit for? Sign, exactly. That's going to go to the adder or adder subtractor, and this is actually how we can use the design of an advanced digital system to improve performance as well as reduce error. So that's where that design comes from. So in this specific case, ALU control is the abbreviation for this ALU operation. If it's 4 zeros, then ALU out is going to be A and B. So we are ANDing all those values. If it's 0, 0, 0, 1, we're going to have OR. Then, as I've discussed, 0, 0, 1, 0 is add. 0, 1, 1, 0 is subtract. 0, 1, 1, 1 is going to be this value. So does anybody, before I tell you what it is, does anybody actually know what that notation means? What does it mean?
A is less than B, put out 1 as put out 0.
Exactly right. So what this means is if A is less than B, then the result's going to be 1. Otherwise, the result is going to be 0. And so in this specific case, that also matches our 0 bit, right? So this becomes useful, and for now, it's just it's an I believe button scenario. But sometimes knowing if it's going to be 1 or 0 will allow us to actually be able to combine instructions. So for example, if I is less than j, then we just have a result. But if I is less than or equal to j, we can actually use the previous result to do both of the comparisons at the same time, right? And then last but certainly not least, and I've limited it just to these values to kind of teach the concept. But here in this case, 1, 1, 0, 0 is equal to not A or B. Right? You got a question?
Oh, no.
All right, excellent. Right. So the actual term for this is known as set less than. If A is less than B, then set the result equal to 1. And so when we start getting into the actual assembly code, you see SLT is the designation. So you're starting to see BEQ, branch equivalent, branch not equal is BNE. So there's a lot of those summaries. So the next topical guide objective is what's going to happen when how we actually generate these ALU control signals. So if you remember from very first lecture, I discussed how a 32-bit control signal for an R-type has a 6-bit opcode. I have RS, RT, RD. I have a shift amount. And then I have this 6-bit funct, and it's a function value, right? So what ends up happening is this value, if it's an R-type, it's going to be all zeros, right? And then I use this function value to determine whether or not it's an addition or subtraction or add. So what ends up happening is that this function value is sent to what's known as the ALU control unit. So if it's 2, right, 6 hex, then it's going to be AND. 2 5 hex or 1 0 0 1 0 1, then the ALU control is going to be 0 0 0 1. 2 0 hex is going to be add. 2 2 hex is going to be subtraction. So that's going to be 2B hex is going to be SLT, set less than, and then 2 7 hex is NOR. So I just want to kind of give you something to think about. I'm going to ask you a question. I don't expect you to know the answer, but I want you to kind of churn your brains here for a minute. Why do you think this TGO is important? Why do you think that if I have these values here, right, I can only send 16 values to the ALU, right? Then why do I even bother with function? Why not just send the function value instead of sending this ALU controller? Why not just send that directly to the arithmetic logic unit? Yes?
Because we want to embed the function, so that it brings you can actually go directly to that versus having to read through a lot of not this, not this.
Okay, you're on the right. It's a good thought. It's kind of on the right path. This is what I want to do. There's no wrong answers here, right? I just want you to spitball, right? Kind of think about it, because you don't know the full data path design yet. We'll eventually get there. So that's a good point. One thing we want to do is we want to be able to make sure that when we generate code, that we want to be able to state the specific function value that we want to go to the ALU. We talked about exceptions and interrupts. So we want to make sure that we check to make sure that our value is correct. Furthermore, I've only really told you about R-type instructions. So, no, I have told you about I-type instructions, right, where you add like B equals A plus 5. So 5 is what's known as an intermediate value. I've alluded to it. It hasn't been a TGO yet. So what ends up happening is it's an opcode, which is the same 6 bits. I have RS and RT. So that would be 5 bits and 5 bits. So that would be, let's see, B equals A plus 5. So this would be AB. And so you see this is 10, that's 6. So that's 16 bits. The intermediate value is the next 16 bits. Which means if I send those, which means physically I'm still sending those same last 6 bits to this ALU controller every single time. So what ends up happening is I have these same values. You notice that they're the same, but I also have 1 0 here to indicate that that's a value that I actually want. MIPS, the instructions are fixed length. This 1 0 indicates that it's actually an R-type instruction, and this is a value that the ALU is actually going to want to pay attention to. So this allows me to not have the arithmetic logic unit do instructions that I don't want it to do. So you're on the right path. It's a very good guess. Yes? Sure.
With the actual, like what the ALU does, let's say with the end or that first most right bit being at 0 or 1, I'm just curious, say if it's the easier operator, let's say it's adding an or and then you have the add subtract skips a bit and goes to the left. Say the 0, 0, and then the NOR would be more complex. Is that the reason for that design?
No, not necessarily. The key thing is that, I mean, and I see where you're going with this. I like the thought, right? So what I've said is that we have this optimization that we can do with add and subtract, and now your next thought is, ooh, what else can we do? What else can we do, right? I like it. There's no actual specific reason other than we just want they have to be in a specific order. The one thing that I've, if I ever had the opportunity to talk to them about, if I was going back, was going, well, hey, if we have this NOR gate, why can't we just say, why couldn't we just have, instead of having this as AND, we can have AND and NAND be opposites, and we can just use inverters to reduce area. But I unfortunately did not design MIPS, but, you are the future. So do it, make a lot of money. Remember Professor Morrison. No. But I like the thought process. That's good. That's the kind of thing that I want to happen in this class. Like, well, wait a minute. This would be kind of cool. Yeah. So I just want to make sure that I'm encouraging those kinds of thoughts. All right. So the next thing I want to go over is floating point addition. So we've talked about, I have 16 and 5, add 1, carry the 1, and it becomes 31, right? So, and I've also talked about how 2 to the 31 minus 1 is greater than or equal to x is greater than or equal than negative 2 to the 31st, right? So this is the range of our 32-bit value. Well, let's say I want to be able to do something bigger than this. Likewise, if you remember in school, you had a calculator and it had 8, or maybe I'm dating myself here, maybe they're much bigger now. But back in my day, you had calculators that had 8 LED lights, right? So if you added 2 8-bit numbers, it was always fun to do that because the calculator would just spit out some stupid value that was clearly wrong, right? It would just be like a negative number, and you're like, why? So what happens if I want to represent a number bigger than that? Well, it's the same thing. We want to use IEEE 754 format, which is the equivalent of scientific notation. So you have 1.31 times 10 to the negative 6. Right? That's really, right? So what happens if I only have something that can represent that, not that many characters? That allows me to go outside the bound of the number of bits. And so that's what we're doing, and that's what's known as floating point addition when we're doing this in binary. And so I kind of give this example here where we're adding two exponents in scientific notation. And then the key thing, and this is going to become important as we go over these examples here today in class, what happens when we have to make our exponents the same? Remember that? No matter what, if you added them together but didn't account for exponents, you got all kinds of funky values. And so that becomes an important consideration in IEEE 754 format. So what is okay, so I know I have the definition up here, but what is, who here knows what the IEEE actually is? Okay.
Foundation?
It's a okay, so yes, it is a foundation. So it's the, yeah.
It sets the standard.
Yeah, it's one of the organizations that sets the standards. So we work with the, there's the International Standards Organization, and the IEEE specifically works on anything with electronics. So it's the Institute of Electrical and Electronics Engineers. And so there's actually an IEEE group here in the University of Mississippi Electrical Engineering Department, right? And so they do a lot of things like help students get scholarships, help students get jobs, right? That's a big thing that they do. But they also set up a lot of standards. And so in this case, the IEEE 754 standard is a format for single precision floating point notation. And so single precision floating point notation is 32 bits. It's double precision, it's 64 bits. So I know all of you have some sort of coding experience. How many of you have coded in C++? Okay, so about 4. Okay, so you'll have dealt with floats and doubles. Okay? So, and you would know that if you printed out the result, you would have different some sort of decimal value for each one. Right? The reason why is because the integer, float, and double indicates how you're actually storing the information. So integer is what we've covered up to this point. 2 to the 31 minus 1 is greater than or equal to x. It's greater than or equal to negative 2 to the 31. That's an integer value. We are using the full 32 bits to represent the number. We have one signed bit and then 31 bits to represent a number. Okay? And so there's no decimals. Single point floating notation is this IEEE 754 format. So that's a 32-bit number, but we're breaking it down to allow us to represent not only decimals, so we have a decimal point, but it allows us to represent the exponent as well. So in this specific case, it's 32 bits just like everything else. The first bit is the sign bit. 0 for positive, 1 for negative. The next 8 bits are the exponent. So we can have positive exponents and negative exponents. And so what we're going to do is when we get down here, this equation, this e minus 127 becomes really important. So whatever that value is, we want to have that subtract, that the architecture intuitively knows we subtract 127 to get the actual exponent. So if these 8 bits are all 0, that means no. It's not no exponent. If it's 0, yeah, if these 8 bits are 0, all zeros, that means that e is 0, and it's 2 to the negative 127. And so if it's all ones, that means it's 255, right? Which means 255 minus 127 is 128. So it can represent everything from 2 to 128 through 2 to the negative 127 in terms of exponents. And so we use the first bit like before for 0 and 1 for positive and negative. And then I have this 1 plus mantissa here. The mantissa is the remaining 23 bits, right? And it's everything after the decimal point. So what you would be able to do is you would have 1.0 let's say we wanted to have this value right here, right? 1.000 times 2 to the negative 5. Negative 5 here is the result of this. So this is negative 5 equals to e minus 127. You take those together, it becomes 122. So 122 is e, which is what our 8-bit exponent is going to be. Now what this mantissa means is that the 1 plus the mantissas, we assume that the first 1 digit is going to be the most significant bit, and everything after that is the mantissa. So a better example would be 1.0110, right? Times 2 to the 0, right? So in this case, using the format, we know it's positive, so it's going to be 0. Then it's 0 here. Using the same thing, we know it's 127. I know from experience it's going to be 1, 2, 3, 4, 5, 6, 7, 0 followed by 7 ones. And then the mantissa, this is the first one, so it's 1 plus the mantissa. And then it's going to be 0, 1, 1, 0. And then you are allowed to put 3 dots and then say 23 bits. So using this format, this allows me to say this number in scientific notation. Yes?
What are all those original ones? All the original ones? You had 0, 0, and then 7 ones?
Yes. What's 27 in binary? 127 in binary. What did you just ask me?
The exponent.
Mm-hmm. So 128, what's 128? If I say 128 is 2 to the x, right? Yes. Right. So then 127 is just that minus 1. Yes.
Is that s, the negative 1 to s?
Yeah, so very good. So in this case, negative 1 to the 0 is just equal to 1. Negative 1 to the 1 is equal to 1. Any other questions? All right, we're going to go work through some examples here. So, but first, 2.14 is the definition of negative infinity and positive infinity. So I talked about this concept of, so this is 255, right? To the 255. So negative and positive, we just set those values, put it all zeros here. That's the largest possible value you can have. And so we just define that as negative and positive infinity. Anything, you can't go exceed that value. And so that's part of the IEEE standard. So let me scroll down a little bit to the example question. All right, so these two questions here is kind of, this will help you kind of walk through and understand the IEEE format a little better. So here I have two numbers. And so on an exam, you won't have to, everything past here is going to be zeros. But my old PhD advisor gave a IEEE addition number where people were going into like the 18th or 19th bit and they were freaking out. If you can add these four, you've demonstrated that you can add, and that's sufficient to demonstrate understanding, right? Everything else, that's why we have a computer to do it. So in this case, we have these, all of these would just be 32 bits together, but this is IEEE 754 single precision format. So using the formula, I'll prove what these values actually are. So in this case, what we have here is, remember, it's -1 times the sign bit, and then we have 1 plus the mantissa times 2 to the e minus 127, right? So in this specific case, that's 1. The Mantissa is 0. And then this, and this is just practice as you continue to work on this, is going to be 255. So this becomes negative 1 times 1 plus 1 plus 0 is the Mantissa times 2 to the 255 minus 127, which becomes negative 2 to the 128. And as we defined in the previous topical guide objective, that's negative infinity. So in part B, this is where things are a little more, you have to demonstrate a little more understanding of binary values. So I do highly encourage you to practice this. If this, being able to figure out anything between 125 and 135 in binary will be very useful for you. And in general, anything between 0 and 225, you should be able to produce in an interview question pretty quickly, right? You don't have to know that the exact values, memorize it like you did in 3rd grade with 12 times 8, right? But you do need to be able to say, all right, if I say, what's the binary value of 64, you should be able to produce it pretty quickly, right? So in this case, we have a 32-bit value here. We have our equation negative 1, so we already know it's 0. Anything to the 0 power is 1, so we automatically know that this is going to be a positive number. Then the Mantissa is going to be 1.0101, right? So what is this actual value? 0101. Here's how you can, this is the quick trick to be able to do this, right? So what is 0.1 base 2 in binary? I heard it from somewhere. Yeah, 0.5, correct? So basically, this is all just continually dividing by 2. So in this case, if we do 1.1101, actually I'll do 0.1111 first, and so if it's 0.1 initially, this first bit is basically you're adding 0.5. Here, what's 0.5 divided by 2? 0.25. So we're going to add that 0.1, and so what's 0.25 divided by 2? 0.125, right? And then again, this becomes 0.0625, right? And so beyond that, things get messy, and that's why I don't put it on exams, right? So in this case, we're just adding 0.5 plus 0.25 plus 125 plus 0.625. So in this case, it's 5, 7, 3, right? 0.9375. So in this case, it's 0101, so it's 0.0101. We don't have 0.5 because that's 0, so it's 0 times 0.5, 0, 1.25 is 1, 0 is 0.125, so it's, I'm going to say that's 0.25, so it's still just 0.25, and then it's 1 here, 0.0625, so this becomes 0.3125, right? So that is how I got this number. So you can, this is a calculation I can reasonably expect you to do off the top of your head on an exam. So in this case, we have calculated this value here. And then likewise, the other thing I can expect you to do on an exam is being able to translate that from binary into decimal. So in this case, it's 128 because, right, the most significant bit. And then you just add 5 here. So 128 plus 5 is 133. Then it's 133 minus 127, 1.3125. 133 minus 127 is 2 to the 6. And then you just do that math and it actually comes out to 84. Yes?
Why is it 0.0101 and not just 5?
So review the Mantissa definition. Okay, so again, 1 plus Mantissa. So the most significant bit is not part of the definition. So if I want to represent 1.10, if I wanted to represent like, actually 0.5625 is a good example, right? So this becomes, you subtract 0.5, so the bit's going to be 0.1001 because it just becomes, you subtract 5, it becomes 0.0625. If I want to represent this in scientific, so this is times 2 to the 0. The Mantissa finds the most significant one and has that out here. So it becomes 1.0010 times 2 to the negative 1, right? The Mantissa is this value here, 0010. This result here, remember, is going to be, if you go back to your equation, it's E minus 127 is equal to 1, negative 1. So that E is just going to be equal to 126. So that becomes 1, 1, 2, 3, 4, 5, 6. Right? So it's 127 is 0 and 7 ones. You subtract 1 from that, it's 126. So then our full scientific notation for that number would be 0, exponent, 0, 1, 0, and then 23 bits. So if it's still confusing you, I highly recommend reviewing this topical guide objective and then going through the problems with that definition. That'll help you out a lot. Great. Any other questions? Okay, so this TGO 2.15, the handy floating point addition algorithm, which you can go through while working on these problems. So the examples 2.2 through 2.4 go over these kind of here. So first, convert the decimal numbers to binary. So if you're practicing and you're trying to get the hang of it, my recommendation is first, and let me scroll down a little bit so you can simultaneously have the algorithm and just an example of the question. You don't need to see the work yet. So here I would say calculate the sum of 0.8125 and 0.25 in binary using the floating point addition algorithm, right? First thing, 0.8125, 0.25, put those in binary. It becomes a little more complicated when I throw a negative number at you, but not that much more complicated. Next, determine the exponent value for the IEEE 754 format for both numbers by using the current exponent, and I put EXP, and using the equation EXP equals E minus 127. Right? So for what that means is if I have 0.8125, that becomes 0.11, I think that's 1101, right? Yep. So this is just times 2 to the 0, right? So that 0 is what I mean by EXP. Plug that value in there. The exponent that goes into IEEE 754 format is the solution there. I'm sorry, that's so if you put in the Mantissa, this becomes 1.1010 times 2 to the negative 1, right? And so that becomes, the E becomes 126. So that's how you represent that there. Right shift the smaller Mantissa. So oftentimes you're going to have some smaller result value by the difference in the two exponents. So what that means is if you have one value that's 2 to the negative 1 and one value that's 2 to the negative 2, you're going to shift them to ensure that they both have the same exponent when you start adding them. And so there's portions where you take that's when you take the numbers out and put them into the arithmetic logic unit. Next step, add the Mantissas. And finally, this is where we take in the topical guide objective from the last class, where if the addition results in an overflow, check the exponents. If they are the same, you just add 1 to the exponent because you've got overflow, right? So if they're the same, that basically means you're going to end up doing a shift. Remember how I told you if they're the same, you can have overflow. If they're different, you can't. So if you have and we see if you get an overflow, that just basically means the number kind of disappears. And I'll show you an example of that type of problem in a bit. If they are the same, add 1 to the exponent and use the overflow as the additional bit for the 1 plus m in the Mantissa. And you'll see an example of that in 2.2. If they are different, if the non-carry bit is 0, and so what this means is if I have a 1.1, right? And so the difference, so you have 0, this carry bit becomes 0, and it's a 1. What I mean by the non-carry most significant bit is that bit there. That wasn't there. This is a carry, most significant non-bit carry. So if it's a 0, it's positive. Otherwise, it's going to be negative. So the next 3 examples are going to be demonstrations of how all of these different portions of the algorithm work. All right, so let's start with 2.2, right? Okay, so I've put more detail than I would expect you to put on an exam. I just want you to be able to see everything that I've done to see how the algorithm works. So in this specific case, first step, we convert to binary. Right? So 0.8125 is 0.1101, and 0.25 becomes 0.0100. Starting to convert it into this format, we have the Mantissa we find here is the most significant 1. In this specific case, for 0.8125, it's 1.1010 times 2 to the negative 1. For 0.25, it's 1.0000 times 2 to the negative 2. So what that means is we have our EXP value, as I notated in the algorithm, is equal to, they're both equal to E minus 127. In this specific case, in 0.8125, E is 126, which is that specific value for the exponent. For negative 2, that comes out to E is equal to 125, and you can just see that if you know that this number is 127, 126 is just that number minus 1, subtract 2, and you get that number, right? So that's where that makes sense. And so the numbers that would be going in physically into the algorithm are these 2 numbers. So that's 0.8125 and 0.25 as represented in IEEE 754 format. So then what's going to happen is these don't match. So just like you did in elementary school, you have to make the exponents match. So here, I know that's 126 and 125. So it allows me to know that the difference is 1. That means I have to shift this by 1, shift right. So an important detail, if you're shifting right by 1 and it's positive, you put zeros in front. If you're shifting right by 1 and it's negative, you put a 1 in front. And so then what ends up happening is that we add them together, right? And so 0, 1, 0, 0, carry the 1, 0, and then we have 1. So there it's the red bit is overflow, and that 0 is the most significant non-overflow bit associated from the equation, right? And since the XORed, we also know that that's the most significant bit. We know that the exponents 0 and 0 are the same, therefore we are permitted to have overflow. And therefore what we can just do is we just do a shift. And so this, instead of the decimal point being here, it's here. So this becomes 1.00010 times 2 to the 0, right? 0 right? Does that make sense? E equals 127. And so then what's happening is our result, and as you can see, I put valid exam answer. Sign bit is 0. 100. Let me scroll up so that way some of you in the back can see. Sign bit, exponent, Mantissa. And you're not going to have anything on an exam that goes over 4 bits. And so what's going to end up happening is you can just put 3 dots and just, I do expect you to indicate on exam that the Mantissa is 23 bits. And then what I like to do is what I did when I took this course back in the day is I would then put this back into the original IEEE 754 format equation. 0.0625 and then this becomes e to the 0, 1.0625, and then we check with the original result, 0.8125 plus 0.25 is in fact 1.0625. Does anybody have any questions about that? I can see that you're getting the exponents and what I'm doing with the binary numbers. I can see it's making much more sense now in your eyes. Okay, that's good. All right, so what's that?
Another curiosity. Later on, when we learn that the string of zeros and ones, would we be using what we learned to like convert that over to ASCII?
Yes. Okay. We won't be doing ASCII in this specific course, but we're going to be doing machine language, assembly language, and I know that a lot of you come up and say that I'm really scared of coding skills. I have assumed that all of you don't have good coding skills. It's a fair assumption. It's not because I think you actually suck at coding. It just means that I don't assume that you're proficient at it. And so I will teach you enough coding to understand what's going on. So in this specific case, what's going on here is we're going to be diving into the mixed string sheet. Right? And so how does this architecture actually work? How does the code that we're writing and how are we actually compiling it down onto an architecture? And what does all that actually mean? So I kind of alluded to C++, and I'll give you some examples later on so that way you all raise your hand the next time you have a course and someone's asked you about it. But the general idea is that different number representations come out in different bits. So in this specific case, if I had this number here, but it was an integer, it would be a really big number, right? I'm not going to bear out to calculate, but using actually, if we have designated that's a floating point integer, the compiler says, no, that the value in this register is a floating point, not an integer. By using the IEEE 754 format, I know it's actually 1.0625. One of the reasons it's useful is because since integer values obviously cannot store any decimal value. Also, this allows me to go beyond the 2 to the 31 value. So that's why understanding this is important. Does that answer your question? Yeah. Any other questions? All right, so 2.3 in this case, so these next two examples, and we'll do these two examples and then you'll be dismissed. I have one case where the smaller value is the negative number, and I have one example where the negative number is the bigger number, so you can see how the result should play out. Right? And in the case, they're both 0.5625 and 0.375. In this case, calculate the sum of 0.5625 and negative 3.75 in binary using floating point addition algorithm. Keep 4 bits precision during the calculations. That's my way of saying don't go more than 4. So I'm trying to reduce your work. And represent the result in IEEE 754 precision format. Show a step-by-step calculation. So in this case, we do the same thing. We convert to binary. And here we have 2 to the negative 1. We do the same thing as before, and we calculate E is 126. In this specific case for 0.375, we have this normal value, but because it's negative, we have to do 2's complement. So we invert all the numbers and add 1 like before. So this gives us 0.1010, right? If it's 0.0110, that becomes 1001, 1010. Likewise. Shift it over to get the Mantissa, 1.0100 times 2 to the negative 1. So here's our notation. You will notice that the sign bit is 1 instead of 0, right? Right shift the second value by 2. Actually, you don't need to do that because they're actually the same exponent. So you can ignore that. So in this case, we add these 2 values. And here, you can see that we do this result, 1.0010 plus 1.0100 gives us overflow and a most significant bit value like before. So if we go back to the algorithm that I presented, 0 means it's positive. And since we have proven earlier in the section that if they have the sign bits are different, you can't have overflow, that can go away. We don't have to worry about it. So in this specific case, our result is 0, 1, 1, 0. We take the Mantissa result, so it becomes 1. So the decimal comes here. It's from 1.1000 times 2 to the negative 3, which comes out to 0.8125. IEEE format. So we subtract 3 here, and then that's our result here. This Mantissa value goes there. That's 1 plus Mantissa is represented in the format. And then likewise, we go back through. 1.5 times 2 to the negative 3 is 0.8175. 0.5625 minus 0.375 is 0.8175. So it works. And then likewise, 2.4. I'm going to go back through and I'll scroll back through to answer any questions after this about 2.3 and 2.4. Likewise, we have the same problem except it's negative 5625 and positive 0.375. So in this case, 0.1001, we take 2's complement, comes out like this. We take out all the way to the Mantissa. Since we're going 1, 2, it becomes 2 to the negative 2, right? 0.375, it's 0.0110, so we leave that alone. 1 plus 1.1000 times 2 to the negative 2, and it gives us these results. 0.5625 was negative, so the sign bit is 1. We add these together. Again, I should have deleted that, copy and paste error. You add them together, 1, 0, 1, and that's overflow, right? So the most significant bit that's non-overflow comes out to 1. The 2's complement, we're going to take the 2's complement, and the result is a negative number, right? So you take the 2's complement of the result, which is 1.0100. That comes out to 0.1011, right? And that's 0.1100. I'm sorry, I'm showing all the steps of the 2's complement, right? So you flip all the numbers and then add, right? So you add them here, and then you shift to get the Mantissa. 1.1 times 2 to the negative 1. And since it's negative 2, you can do the math here to come out to 125. And then here. I'm sorry, 124. So you do the math again, and that's actually the negative result is correct. All right, so we still have 2 minutes. Does anybody have any questions about the execution of 2.3 or 2.4? All right, well, I think you, I guess.
So when you're getting, you said the Mantissa, you shift over, so like, where you have a 0.1010, and then you shift it over to
yeah, the most significant one, correct. So the question, hey guys, I know you all are anxious to leave. So the question is, and this is a really important concept, so we'll just go over this again with 0.5625. So all of the questions I've been getting today seem to revolve around the same idea. The Mantissa, the reason I have the definition as 1 plus m, you find the most significant one, and that's the 1 value. Everything after that is the Mantissa. So in this case, 0.5625 times 2 to the 0. If you're to do this to get, it's 1.0010 times 2 to the negative 1. So the IEEE standard was defined this way specifically to indicate this value. Okay, any other questions? All right, now it's 10:45. I have to dismiss you.